Hey folks, doing the energy rant from my lab today, otherwise known as my garage. Last week I was telling a colleague about how I was studying up on phase change materials, and I learned that water in containers or salt water, whatever the phase change is. By the way, a phase change material is something that changes phase from liquid water to solid ice and back. And there's different variations of it. Salts, hydrocarbons, which are also known as paraffins or fats, vegetable oils, and things like that. A lot of things change phase. Coconut oil, for example. Anyway, so I learned that water doesn't necessarily freeze in a container at 32 degrees. It requires some subcooling, depending on the impurities, the container, the shape of the container, and things like that. So what I'm going to do today is I'm going to look at how those several different variations of water that I have will react, and how cold I need to get them before they'll freeze. And so I'm looking at 6 different mixtures of water. I'll call it, or 6 different samples. First, I have bottled water from the store. So I'm going to use bottled water. That's one sample. Another sample is I'm going to open one up just to take any pressure considerations out of it. Expose it to a little bit of air. Another one is going to be distilled water. Another one is going to be tap water, right out of my tap in my house. And then I'm going to have soft water that went through the softener in my house. And then I'm going to have melted snow. The reason I'm going to have melted snow is snowflakes form around, or they start to nucleate, or water condenses around basically a speck of dust. And that's what water and snow all nucleates around a speck of dust. So that'll have some impurities in it. And so we'll see if that one freezes first, or how things go. So I'll bring you over to my test bed over here. So I've got, we're starting out with just ice water. Well, actually it's snow and water. And I have my Fluke infrared thermometer, which any self-respecting engineer, any good cooks, this is a great thing for cooks to have, because you don't have to stick a thermometer in anything to tell what the temperature is. So we've got just ice water at 30 degrees, and to be honest with you, there's a little bit of salt in there. So yeah, it's a little bit below freezing. So we will see how it goes. So I also want to know how water with impurities in it, which is snow, will stand up to freezing. And oh my God, it's a gas stove! I'm gonna die, apparently. Oh, I'm getting lightheaded. I better turn this off. Well, I'll see you later. Alrighty, folks. So here's the water that I bought last night. We have the Earth's Perfect water from Chippewa, and we have distilled water. And it's about 22 degrees in here. Not 28 right now. I guess it warmed up. So anyway, let's take a look at what the temperatures of these are. 31 degrees. Okay. Clearly not frozen. 29, whatever. And this baby is 28 degrees and clearly not frozen. All right, so heads I lose. So let's carry on. So people have done these tricks on the inner tube before. You can look it up yourself. Water flash freezing, and it flash freezes slush into slush once there's a way for it to nucleate. So nucleation is a way that the process starts freezing. And once it starts freezing, the crystal shoots all the way through the water. So all you need to do is start the freezing process, and the whole thing will be frozen into a slush and come into equilibrium back at 32 degrees. And so what I'm going to do this experiment is I'm going to add salt to the ice water over there. Everybody knows that salt melts snow and ice, but I think what most people don't know is it also makes it colder. So it lowers the melting point, and that's what, that's how you control PCMs and phase change materials. For thermal storage, you add or subtract salts, basically, to get a freeze point at 5 degrees or 10 degrees or minus 20 degrees or whatever the need is. So you just adjust the salt solution in the mix, or there's other phase change materials as well, including hydrocarbons, or what I call hydrocarbons, are sometimes known as paraffins, waxes, fats, vegetable fats, and things like that. So I'm going to mix some salt in the solution, and we're going to drive down the temperature, and I'm going to put all these sampled bottles in there to, we'll see what freezes first, and we'll see if we can break something. So anyway, I've got the distilled water here on the shelf, on my bench, and we can see that it's still liquid, and it's like 28 degrees. So I don't want to miss anything. So I'm going to take the cap off. See what happens. It's trying to be okay. Still liquid, obviously. Okay. Okay, dudes, we're underway. I was surprised how much salt I had to shovel in there to get the temperature to come down a lot. So anyways, it's about 27.5 degrees, a little bit more, 28 maybe. We'll see if that is enough to freeze. By the way, I put in an open thing of water there. We'll see what happens there. That'll be the first one to freeze. You'll start seeing ice crystals around the edge there, because there's a place to nucleate along the edge, along the open surface. You'll start seeing crystals on there before any of these bottles will freeze, I'll bet. Anything. So the numbers on them are just so I keep track of which is which. Like one is unopened bottle, and two of bottled water, and two is, I just pop that open just to release pressure, and I don't know what the other ones are. I'll come back to that later. So this must be like ice fishing, where I'm sitting on a 5-gallon bucket, sitting here looking at this hole and waiting. It's like watching paint dry, but I'm waiting for this stuff to get cold. See what happens. So interestingly, I just put some salt on the ice. It gets really cold when you do that. 23 degrees, 16 degrees. Wow. Okay, folks, so the theory is, if you jostle the water a little bit, it'll kick off the nucleation, and it'll flash real fast. So I've got bottle number 5, which is the melted snow. I predicted that'll be the first to freeze. So I'll pull that out, see if it's frozen at all, see what its temperature is, see if it's frozen, and I'll just smack it on the floor a little bit. Okay, so it's, believe me when I tell you, it's 29 degrees, 29.5 degrees. Still liquid. So let's try this out. Nothing. Still nothing. That's some tough water. 28 degrees. Wow. All right, put her back in there. Okay, number 3 is the tap water. That is at, let's see, it's still liquid, and it is at 27.4 degrees. And very much liquid. Can't get it to freeze. All right, let it go. So like I said, the water in this thing, the open water, is 30 degrees about. And you can see You can see the ice starting to form around the edge. Because it's got a place to nucleate. See that? You can see that right over there. The ice is starting to form around the edge. 30 degrees. And I can't get these friggin' lump masses of water to freeze at 27. Well, crap. I already missed number 5, froze first. That's the snow water. I already missed that thing. It's already frozen. So I blew that. It's got the crunchy ice in there. And that is at 31 degrees. So as soon as it freezes, the temperature will rise to the freezing point. As soon as it starts freezing, it all comes into equilibrium at the temperature, at the freezing point. So that's a bummer. I already missed that one. Let's see. Let's look at number 2. I predicted that one would freeze next. This one is pure liquid yet. It's 25 degrees, 26 degrees. So let's see what happens. Oh, it's freezing. You can see the slush forming on top. Look at that. Pretty cool. It's heading on down now. See that slush up here? Clear water down there. It's freezing right before our eyes. Oh, pretty exciting. That's what I predicted would freeze next. It is, well, it's the opened bottled water. Yeah, there you go. It's freezing right in front of your eyes. Not even adding any heat or taking any out. It's 32 degrees up there, 31 degrees down there. Pretty groovy, eh? So that was subcooled to, well, I don't want to remember what it was, 26 degrees, something like that. I'm just going to leave that there. You can just watch that baby freeze. This one, this one already crystallized. So it's like, I missed the slush. So this is what I was trying to do. I was trying to show the slush and watch it freeze in front of your eyes. Let's see, unopened, opened, distilled. I think the distilled will be last. 6 is soft water. That's probably already frozen. Let's pull that out and see what happens with that. Nope, that's liquid. It's liquid at 27 degrees. 27 degrees. Think that'll freeze in front of our eyes? I bet it will. I wanted to get one to freeze really fast because I've seen these freeze like whoosh, like instantly. I can't tell. I'm gonna watch it a little bit. Let's see the temperature. It's 28 degrees. Oh yeah, I think it's starting to freeze. Man, it's slow. Yeah, you can see the slush form. You can see the slush forming up here. In fact, I can see crystals in there. If you look hard enough. See a crystal right there. Jostle it around a little more. Get an air pocket in there. Yeah, I can see crystals in there. So that's freezing. It's now 31 degrees. See, it warms up. As soon as it starts freezing, the freezing gives off heat. So it warms up. I think that's that one. Thank God the thing's recording. I'd be bored. Let's see. Got a lot of ice in that thing. Let's see what. Okay. I want to let one get really cold. I want to get. Well, I don't want to miss it though. I already missed one. Let's see. 4 is distilled. That'll be last. 1 is unopened bottled water. 3 is tap water. Plain old tap water. So it's hard water. It's not softened. So let's check out 3. Hell, that's already frozen. I already missed that one, baby. Jesus, this thing's frozen pretty hard already.
So that baby already flashed. 32 degrees, of course, because it's a mixture of ice and water. There's that one. So let's go back and look. What's the last one I looked at? I don't remember. So you can see clearly there's ice in there. Yeah. It's ice in 5, which is the snow. So the snow, like I thought, since snow has impurities in it, so every snowflake when it's made, is whether it's rain or snow, they all nucleate around a speck of dust. So there's, it's full of impurities. So naturally that one's going to freeze first, which is what I thought. So we have 4, which is distilled, and we have unopened bottled water in number 2. No, I'm sorry. Yeah, no, in 1. Unopened bottled water in 1. All right, so let's check out 1. By the way, what's the temperature of the bath? Temperature of the bath is 25 degrees. Okay. Number 1 is not started to freeze yet. It's crystal clear. Pung alert. It's 25 degrees. Woo! This could be good. Well, 27. I don't know. Whatever. Let's see what happens. Let's see what. I don't see any signs of freezing. 27 degrees. 28 degrees. See, this is the one that I predicted would be one of the last ones to freeze. I think the distilled one was the only one left in there is still the other one that's not frozen. So this baby's all liquid water yet. 26 degrees. It's not. Man, that thing's cold. Okay, well, I'm going to keep jacking and putting the salt in there, and we'll keep jacking her down. Meanwhile, the freestanding thing is got more ice around it. Yeah. It's forming ice. Believe me when I tell you. Okay, I pulled the distilled out of the bath, which is on the surface is 23 degrees. This thing's 20. It warms up as soon as you pull it out. It seems like 27 degrees. So I think I'm gonna have to get this really cold before it freezes. Really cold. Okay, I'm gonna go back to the unopened bottle of water. And it's still 100% liquid. I wonder what would happen if I opened it. It'd be funny. That could be cool. So that's at 24 degrees, dudes. 25, 24, 20, 20, 20, 25 degrees. I'm going to open this up. We'll see what happens. Not a damn thing. I said I can tell. God, it's cold. Whew. On the hand. Wow. Oh, there it's freezing. There it goes. Right there. Now watch. See it? You can see the ice, the crystals going on down through the right on down through the water. it'll be 32 degrees. It'll switch from 27 to 32 degrees. That's pretty cool. I wish I'd get one to flash. Like, I'll have to see. I'll see if I can get. I'll do another one where I can get it really cold and have it, freeze all at once. Just like zoom, really fast. Yep. So it's slush. Check it out. See the ice in there? Obviously now it's sticking out. It's 32 degrees. Who would have guessed? All right, we got the last holdout, the distilled, which I knew was going to be last because it doesn't have any nucleation sites in there to take off. No impurities. It's going to be a brute. We'll see how cold that baby. Oh, I think that already switched. Yeah, that already flipped over. I missed it. Too bad. Once it's gone, it's gone. Well, we missed that. So what I'm going to do, I'm going to come back. I'm going to put a cold, you know what? I'm going to put a new bottle of that water in there. And we'll see, we'll get it really cold and see what happens. Hey dude, so I still really want to flash freeze something. So I put in a lot of salt into this baby. It's at 20 degrees. And the thing I learned is you got to really stir it up. You got to stir to get the salt dissolved in there. So it's about 20 degrees. I'm going to put in a bottle of water and we'll see what happens. See, what's interesting is there's ice and frost and forming on the outside of the tub. So let's, I'm going to go ahead and check that out. We'll see how cold it is. The water, bottled water, and see if it can do something cool here. Right, still totally liquid. Hold on. $22 degrees. 22 degrees. That's like 3 degrees or so colder than I have the rest. Whew, that's a stubborn model. What would happen if I open it up? Now it's 24 degrees. Takes a while for the heat transfer to go through the water. The bubbles aren't enough to get it to go. Man, it's cold. Okay, we're gonna try this again. Like watching paint dry. However, it's getting cold pretty fast. A few minutes. This baby is 21 degrees. Jesus, that's cold. There it goes. See it? Look at it. Look at that. Look at the ice crystals. Wow, look at that. Oh, man. That is awesome. Swing. It's all slush now. That was groovy, man. So that's all really cool, Jeff, but what's the point? The point is, if you want to make ice at 32, you don't want to have to cool it to 22. Or if you want to make ice at 10, you don't want to cool it to minus 10 to get it started. There are lots of ways to mitigate that and bring the nucleation temperature up closer to the freezing point. And
that's what it's all about.